Hello. In this video, we're going to be making yet another animated GIF for Wikipedia. The animated GIF for this video will be a GIF that shows the aliasing effect. So what is the aliasing effect? So when you have a wave, such as this, which is a pure sine wave, it has a corresponding Fourier transform. So here we're plotting the wave on the left and the Fourier transform on the right. We're sweeping the frequency of the wave, which is given by this indication in the top left, and then we're plotting how the Fourier transform of that wave evolves. What we're then doing is we're then sampling this wave at some frequency. In this particular instance, we're sampling it at 10 Hz. So for every second that the wave exists, we sample 10 times. And what we can see on the bottom right here is the corresponding discrete Fourier transform of that sampled wave. And as we can see, as the frequency of the original signal increases, the number of samples along that wave remains the same, but the shape of the wave changes drastically. So what I've done here is the faint orange curve is what you would get if you used a reconstruction algorithm. So you took the frequency given by this point here, and then you reconstructed a perfect sine wave from that frequency. What we can see here is as the frequency increases, the ability to reconstruct the wave still exists because we still have a unique point in the Fourier transform. But once the frequency of the wave exceeds half the sampling frequency, which would be here, so this would be around 5 Hz. So this frequency here is 5 Hz. Once the frequency of the original wave exceeds that 5 Hz, the wave folds back on itself, so we're no longer able to recreate the original wave. There's now an ambiguity, so all these sample points here on the original wave would actually give you a wave of a much lower frequency, and that point is mirrored around half the sample frequency. So you can only reconstruct the original wave if the original wave has a frequency component less than half the sample frequency. Or another way to put it, you need to sample at least twice as much as the highest frequency of interest in your original waveform. And so why are we doing this? Well, if I jump over to the Wikipedia page for aliasing, we can see we have some nice pictures, which is always a good thing, but one thing we don't have is many animations. So if I scroll down, so it gives you lots of the mathematical rationale behind it, gives you plenty of examples, and the closest one that really comes to it is this one. So you can see here you have the original wave in red, and then you have sampled points in black, and you can clearly see that if you were to reconstruct a pure sinusoidal wave from the sampled points in black, you would end up reconstructing the wave in blue and not the original wave in red. So once the frequency in your original signal exceeds half the sampling frequency, you no longer have the ability to regain the original signal. There's ambiguity. You could do the blue wave, you could get the red wave, you could get one that's twice as frequent as the red wave, etc. You no longer have the ability to reconstruct the original wave unambiguously. And just scrolling down more, I don't see any useful animations. There's one here, but just looking at it, it's not immediately clear what's happening. After reading the text, you sort of get what's happening. It's showing 1, 2, 3, 4 different waveforms, and it's changing the sample rate at the top. As the sample rate decreases, you lose the ability to reconstruct some of the waves, with the lowest frequency waves surviving the longest because they require less samples, etc, etc. But to me, that's not immediately clear. So I think this Wikipedia page could do with another GIF, and the GIF in question is going to be the one that we've just seen. So a nice GIF that shows something like this. So as we're changing the sample frequency, as we're changing the input frequency, we're going to see what happens to the sampled waveform. How we'd reconstruct a wave from that sampled waveform, just to show how it's aliased back in on itself. What might be interesting as well in this video is if we extended this animation, but not for the purpose of Wikipedia, but for the purpose of our learning, if we extend this animation so it shows what happens as we just keep increasing the frequency almost indefinitely. As you would see that it continues to fold back in on itself in a forwards and backwards fashion, with each time associated by a phase reversal. The sign of this sine wave changes, which you can see every time it crosses fs over 2 or 0. So we keep watching, the sign is negative, now the sign is positive. And when we go back to 0, you'll see another phase reversal in which we have a positive sine wave, which we'll go back to a negative sine wave. So let's get started. The first thing that we're going to want to do is to do some imports. So this is pretty standard, numpy, scipy, etc, etc. And then also some of the required things from matplotlib to actually be able to plot these things. And finally, FFT and stats from scipy, which will clear in a bit. We'll go ahead and change some default parameters. So make sure the font size is nice and big at 18 and the axes line width, so the bounding box of the axes, the spines are nice and thick at 2. Set up some display variables, so we'll have FPS, which will be our FPS of the plot. The first thing we're going to want to do now is to say I want a wave, so I don't want the top wave to be aliased. So if we go back and look at our animation, you can see that the top wave needs to remain nice and sinusoidal, and so there can be no aliasing on the top wave because we're going to pretend that this is an analog wave, and so does not suffer from aliasing. That's infinite bandwidth. So we're going to have 100,000 points on our wave. We'll go ahead and create that. We'll also add a Tmax variable. So even though we're only showing 1 second, we'll actually go ahead and do 100 seconds, and that becomes a bit clear later on because the frequency spacing in the Fourier domain is 1 divided by Tmax. So we're going to get 0.01 Hertz resolution, even though we're only then going to show 1 second. It gives better resolution, so smooth animation. Go ahead and work out our dt, which is simply the difference between two of those points. Next, what we want to do is add some resampling. We're going to resample the original wave 1,000 times rather than 100,000 times. Go ahead and create that. And we can also pull out the difference in time for the resampled wave. Next, we want to work out our frequency. That's quite easy. So in our frequency domain for the top t vector, it's simply going to go from 0 to 1 over dt. So remember, 1 over dt is our sample frequency, and the length will be the same. We can also pull out the difference in frequency just from that array and do the same for the sample frequency. Next, what we want to do is we want to decide what we want from our plot. So if you look at the plot, you'll see that it started off quite fast. So it was changing this frequency quite rapidly. And then as it gets towards the interesting stuff, which happens at fs over 2, it starts to slow down. And then as we keep going, it speeds up again. So we've not got a linear sweep of frequency. And to do that, I've got a nice way of doing this. So we want a function in which the middle portion has more points than the outer portions. So think of it like when you do numpy.logspace, for example, you have equally spaced values in the log domain. What we want is non-equally spaced values in the time domain with a preference for values around the middle. So we can go ahead and do that. So we're going to do it using an error function. What we'll do is we'll say the standard deviation of our error function means that we have basically 3 standard deviations on each side of the central value to our extents. So it's 3 sigma away from the middle. The middle will be simply the average between the x min and max. And if you're not following this, don't worry, we'll be doing an example of this momentarily. So we'll have a distribution, we'll call scipy.stats. We'll do truncated normal, and that accepts a value. So basically it's a normal distribution, but truncated at 2 limits, a and b. And a is actually given by this. So these are in standard form, so they need transforming. It takes the normal location scale parameters. So the standard form just means that it takes location scale parameters. It's not just, for example, if you went on Wikipedia and looked at the formula for the truncated normal, it's not just that formula. Now here's where the magic happens. We do the distribution and the PPF, so that's the point percentage function. So that takes in values between 0 and 1, and it gives you the variate associated with that probability. So if you think about a CDF function, it's the inverse of a CDF. But why is this special? So if we now do a linear space between 0 and 1 with the same number of points n, let's go ahead and plot that, plt.plot, so we'll just call matplotlib. We'll just go ahead and plot earth space. Earth is error function, by the way. So earth space, we'll say between 0 and 100, 132 points. We'll just see what it looks like with the normal scale. Create a linear space from 0 to 100 and step to 128. Then go ahead and compare that to our error function space with the same parameters. Remembering, of course, that the b parameter is the max. Go ahead and plot that. You can see here, so on the x-axis, think of this as the index. So it goes from 0 to 32 basically. Or there's 32 points along the x-axis. And then if you look here, on the y-axis, you see we get a non-uniform distribution of points. So you see that more of the time is spent. So for example, if you took this middle third of the data, so in the middle third of the indices, we see that more of those indices are spent around this region here between 40 and 60, which is what we want. So we're going to have big steps initially when we first start changing the frequency. Then we're going to have smaller and smaller steps as we reach the middle. So when the interesting things start to happen and the two curves start to cross, before speeding up again, going towards the end. Let's have some frames. So we want to do 600 frames in total for animation. Seems reasonable, 10-second animation. And then for the plot, we want to sweep the frequency from this resampled frequency, the first index, the resampled frequency, last index. So if we look at our F resampled, it goes from 0 to 9.99 hertz, which means that this will go from 0 to 9.99 hertz. And if you look at the plot, you can see it takes big steps at first, so that's taken a step of 0.036. As we get towards the middle, the step is considerably smaller at 0.015-ish. So it's decreasing the number of steps, decreasing the difference between frequencies. And then we can do something a bit more intelligent here. I'll comment this out for now. We'll come back to that because we'll see something interesting happen later on. And now it's the fun part of creating all the plots. So we need 4 plots in total. So we'll do fig.ax, so figure in axis equals plt.subplots. It's going to have 2 rows and 2 columns. It's going to have a constrained layout, and we're going to have a figure size of 12 by 8, so it's going to be nice and big. We're also going to do share x columns and share y columns. So what does that mean? It means the x, for each column, they will share the same x and the same y, because each column shows the same plot. On the left, or the left-hand column is going to be the time plot, so signal versus time. And on the right, it's the Fourier plot. So it's going to be Fourier amplitude versus frequency. We'll then create a lines object because each one of these plots will have one line that we want to change for an animation. So we'll create an empty NumPy array with data type object, and it's going to have a size of ax. So ax is a 2x2 array. So that's a quick way of creating that. And then we just need to go across and do things. So let's create our lines like this. So the lines in the top left plot, so that's the 0 row, 0 column. And that's going to be equal to an axis, the axis in that same position, so top left. And then for now, we just plot nothing. So we have blank lines in there. Let's have a line width equal, let's create a variable called line width. Line width equals 2, and we'll put that in there. Color equals, let's do the top left as blue. So the non-sampled waveform will be blue, and the sampled waveform will be orange. Let's see what that's complaining about. Complaining about that. So that's that. So let's just go ahead and put that. It should have created 4 plots for us. 1, 2, 3, 4. Very good. Nice thick borders on the outside. And you'll see that it shares the same x-axis for both the columns. So there's only one axis drawn on the bottom. Very good. Now we need to set the limits. So again, x00 set xlim, and that's going to go from t0. And remember, we only want to display 1 second. So we'll create a variable called tDisplay. Put it up here. 1 second, and that would set that. And then we'll do the same for the y-axis. And let's go ahead and just create a variable for that. So we'll call it ylims. Let's go -1.2 to 1.2 because we're plotting sinusoid, so they're going to go from -1 to 1. We need that little bit extra just because we're going to put some text object on there. And then we just need to go down and let's set a grid, slightly transparent grid. And let's set a label. So this is going to be Y, so the signal Y. I'm going to plot that. You see our top left plot is now set up. It's got the time going from 0 to 1, and it's got a label of Y. So next what we do is we just go through all the other plots and make sure the labels are set up. I'll just copy and paste this over. We'll also create a variable called ylims FFT. And we'll give those something reasonable, so I think that should be half of this. We'll do -0.6 to 0.6. Go ahead and neaten all that up. Plot that. And you see we've got everything we want now. So if you look here, on the top, we're going to have our original signal with its Fourier transform. On the bottom, we're going to have our sampled signal with its Fourier transform. You notice as well that I've done the Fourier transform relative to the sample frequency. So that was achieved here. I set the x-ticks manually to 0, half the sample frequency and the sample frequency. So this is the f_resampled, which remember goes from 0 to 9.99 hertz. But by doing this, and then labeling it as 0, fs/2 and fs, you get rid of needing to actually explicitly say what the frequency is. And things like this, we're going to put the imaginary part. So the Fourier transform of a sinusoid ends up as two imaginary components, one positive imaginary, one negative imaginary. So by plotting the imaginary part, we're going to get just the amplitude basically of the sines. We could have done this with cosines, but I quite like sine a bit better because it starts at 0. And then to do the things like this, so the fancy symbols, you can just write a latex expression. So that's all a latex expression, remembering to escape the backslashes. So backslashes need escaping if you don't do raw strings. So I think that's pretty good. Next, we need a few more things on the top left. If you remember from our animation, we're going to need a display here that shows us the frequency, and we're also going to need a scatter plot that shows us the sample points. So the display frequency is quite easy. So what we can do is on the top left plot, which we know is that one, we create an object called text, and that's going to be equal to this object on the top left. So this axis on the top left dot text. We'll give it a position of 0.01, 0.99. We'll give it a blank expression for now. We'll horizontally align it to the left. We'll vertically align it to the top. We'll make sure that it's relative to the axis itself. So we don't need to actually worry about the values of the data. So whether the data goes from 0 to 1, 0 to 10, for example, whether it goes from minus 1.2 to 1.2 or minus 0.5 to 0.5, doesn't matter. By doing it relative to the axis, it will always remain there. And the advantage of doing this as well is that now this is an object that's drawn inside the axes. So when we do our animation, we can enable blitting. We can clean that up. And then for the scatter plot is very easy. So all we have to do is scat, we'll call it scat 0, so scat for the top plot, and it will be a scatter plot attached to the top left axis. And for now, we don't plot anything, but we do need to make it the right colour. We'll leave the options as default, go ahead and plot that. Nothing's broken. Text object is probably there, just can't see it. Likewise, we need a scatter plot for the bottom as well, so we'll go ahead and call that scat1. Scat1, making sure that it now reflects on the bottom row, so 1, 0, and that should be our two scatter plots ready to accept data. I actually think that's most of the things we want to do now. So that's just it's a lot of code, but just setting up the plot basically. Just things like setting the x limits, setting the y limits, setting a grid, setting some labels, etc, etc. Remember, we also created this lines array. So we've got this lines matrix. So we've got this ax matrix, which is a 2x2 matrix of axis objects. So physically in the plot, these are each of these objects here. They also have a lines matrix, which again is a 2x2 array, which is going to be each of the main lines in each of the plots. And to update this, we need a function called update, and that accepts frames. Every time the animation calls for a new frame, it sends a variable I, which we'll call frame, so that's current frame number, and it also needs to know what to do for each frame. So how does the data change? And because we'll be using blitting, we need to make sure that we send back the objects that have changed. So blitting means it ends up being very fast, but we do need to tell it which objects actually change. It's not smart enough to figure that out, and it requires a list of objects. So if we look here, so if we look at our lines is a 2x2 matrix. If you imagine now, lines.flatten, that will create a 1D matrix, and then if you flatten and do toList, that now creates a list of lines to change. That's how we get that. We're also going to change the scatter plots and the text object, so we send all of those back. Now we need to decide what we do inside of the update function. So the first thing we need to do is get a frequency. The frequency equals, and because we've done this intelligently, we can just do fplot frame. Because if you remember, f_plot, it simply went from 0 to the resample frequency of 9.99 Hertz, with more of those values with a smaller step towards the middle where the interesting things happen. So we can just pull that straight out. The frequency is equal to that variable. But then you create a y variable. So what actually we're going to plot, so we want to actually plot the sine of that frequency. So I've done that here, and I've also done minus sign just to spice things up. Likewise, we'll do the resample. So y is going to be a sine function sampled at the times t. Remember we said t is basically a very big array that we know is not going to be aliased within the scope of our animation, but y resampled is based on t resampled, which we know is going to be affected by aliasing. So this is just a way of doing it so that we don't get the effect of aliasing on the original t array, because really what we're doing is saying that there is a signal which is a sinusoid. It can be evaluated at any point t, and so it will never be aliased, but because we're on a computer it has to be discrete, so we have to put in a value for t basically. There are some ways of doing this. Things like SymPy will come with functions where you can plot values to arbitrary precision, so it doesn't matter, it wouldn't matter what extent you use for your t values, for example, you would always get a sinusoidal function that would never be aliased. That's well beyond the scope of this. And now we can do the FFT. So the FFT of the original signal, so scipy.fft.fft, so that's the one-dimensional FFT acting on y. Then do y resampled FFT equals scipy fft.fft of the y and resampled. Okay, let's not do any more here. Let's just come back and actually change those things in the plot. So remember lines 0, 0 at the top left. And there's a function called setData, and then you just give an x and y array, so t and y. You know what, let's just plot that for now. See what happens. Nothing happens because there's one more important thing, we need to run an animation. So animation's very easy, Annie. At the top, we imported this function animation from matplotlib animation. And if you scroll down, it needs a figure, which we called fig. It needs a function, which we called update. So this function is called every time a plot frame is to be redrawn. And then we can give it a frames. So by default, let's just give it a manual range of frames. So n frames. And then repeat equals, let's do true for now. We want to enable blitzing. That means it should only redraw the things that have changed, that we have told it has changed. And that's an interval equals 1000 milliseconds divided by the FPS, which we had at the top, with the value of 60. So if I go ahead and plot that, now we should see we have an animation and it's doing exactly what we want. It's nice and smooth, so it's a silky smooth animation, probably is reaching 60 FPS or very close to it, thanks to the blitzing, and the frequency is changing. And you'll notice that the frequency change has slowed down towards this middle section, towards this middle 300 frame, and it's speeding up again. So it's doing exactly what we want. Let's go ahead and change the other lines. So remember lines 1, 0, so row 1, column 0, and that will be our resampled data. So it has to be t underscore resample and y underscore resample. Plot that. So you see now we've got both of them. You can really see how the resampled waveform suffers because it's drawing straight lines between each of the resampled points. Well, we did say we wanted to see those points, so this is easy as well. So remember we had our scat object, so scat 0. There's a function called setOffset, so it's not setData for some reason, it's setOffset, so I'm not really sure why it's different for a scatter plot, but we have setOffsets, and all we have to, and even more weirdly, it doesn't accept two 1D arrays, so you can't just give it a t and a y, you have to give it a n by 2 matrix, so 2 column matrix with xy points. Easiest way to do that is to vertically stack the two arrays you want, so we vertically stack t and y together, because they're row vectors, and then we simply transpose them so they become a column vector with n by 2. Go ahead and plot that. Okay, that didn't work because I did the wrong thing. Remember, we're doing the resample points, not the original points. Sorry, my bad. Resample points, and there we go. We have our resample points along the curve. And if we look at the original GIF that I showed at the beginning of the video, we see that we need to make them orange on the bottom one, but we sorted that out when we did the scatter. We can just do orange here. And again, let's just copy and paste that because these scattered points are going to be the same on both the top and bottom plot. Let's do is a copy and paste job. And there we go. That's looking really nice. Now we've already calculated the FFT, so now it's just a matter of a slight copy and paste job. So we change the column number. We're no longer plotting t, we're plotting f. We're no longer plotting y, we're plotting the FFT. And here's where something interesting will happen. We'll get something quite interesting. You see, we can't really see much, and that's because the default implementation of scipy FFT does not scale, so it will be n times the magnitude of the original signal, and so we need to divide by the n. So we have our, remember we have our n and n underscore resample, so the FFT if we divide by n, the FFT resampled if we divide by resampled n, it will now be normalized. Okay, so that's what we've got, but you see we have something very interesting happening. It's doing some weird flashing. And there's a very good reason for that. When I said at the beginning, towards the beginning of this tutorial, we had this situation here, where we created an error function space. So if you look here, it slows down its increments as this frequency approaches fs over 2, and then speeds them up again. But you see, our increments are arbitrary. We only specified the min and max. We don't know if they lie along whole numbers of frequency increments. So the original sample frequency interval is 1 divided by t. If we look at that, df is equal to 0.01. If we then look at our f plot, the increment here is not in steps of 0.01. So what we need to do is if we make sure they're in steps of 0.01, this will work. But the reason it's flashing is because we're not sampling at a whole frequency interval, is that what's actually happening is we're getting components that are not quite in the same plane. So it's not just imaginary. And we can just quickly see something here. So if I plot the absolute value of the FFT instead, you'll see another interesting artifact up here, is that this line actually tends to bounce. But it's not just bouncing amplitude, the area is maintained. So the amplitude looks like it's bouncing, which it is, but the area is maintained because there's a theorem called the Plancharel Theorem, which basically states that the integral of the area of the original function should be equal to the original function squared should be equal to the area of the Fourier transform of that function squared. So the square area of this function is changing by virtually nothing. So if you imagine there's a lot of waves that appear over that 100 seconds, and then in the frequency domain you see we're oscillating now between two frequencies. So we have our fixed frequency spacing, and what we're saying is, well, actually we're trying to evaluate a frequency on our original plot that is not an integer number of this frequency spacing, so it oscillates between two. And so what you end up doing is it basically just oscillates its area. So the area is basically the same, but it's just oscillating an area between 2 points. Now, if we add in our little guard up here, which basically it divides it by df, so our frequency spacing, casts it to an integer to make sure that it's an integer number of frequency spacings, and then times by df, so that our f plot is now guaranteed that each value in the f plot is an integer number of those frequency spaces, so it lies on an exact interval of our frequency domain. Let's go ahead and plot that. You see now it stops jumping, it moves completely smoothly along, which is exactly what we want. We do have a bit of a problem, is that it seems to be changing amplitude a bit, which is fine, because I said earlier we just need to take the imaginary part of this, and we can do something even more special. Let's do the sine of the imaginary part. So remember, it's either positive or negative, and then times the absolute value. This will just make it more stable because the actual phase on the Fourier domain changes slightly, so it will oscillate just ever so slightly from the imaginary axis, which causes this amplitude change. And so by doing this, we stabilize the amplitude change but maintain the sine, because it doesn't actually change that much. It doesn't ever change to the point where it becomes completely real. So if we do that for both of them, let's just look what happens. There we are, we get something very, very nice. And I think that clearly shows the Aliasing effect. But one last thing we should really do is, well, let's plot a sine wave along here. So a reconstructed sine wave, because if you read the spectrum, you can read this and say there is a frequency here of whatever, SF times 2/5, FS times 1/2, for example. And then you can reconstruct a frequency from that. So it's the lowest frequency that can be reconstructed from the points. So we go ahead here, and in our bottom left plot, which is where it will exist, so row 1, column 0, we do this thing called line recon, so reconstructed line. Again, nothing special about it, apart from the fact that we now use dash dot, set some alpha, and we give it a color red. And then in here, line recon dot set data, we definitely want to give it t. And then we want to be able to say, so let's just give it a sine wave, so the minus sine wave. And let's create a variable called frecon, where we basically extract that reconstructed value frequency. And that is given by this expression. So it's going to be, so what we're going to do is we're going to look at the resampled frequency array, and we're going to look at the middle proportion of it. So basically the Nyquist frequency, the fs over 2. If the frequency is less than that, then we can simply return the frequency. If the frequency is more than that, then it basically needs to be folded. So it needs to be the expression, it needs to be the minus total frequency, so minus the 10 Hz plus the frequency of interest, which will make it then start going in the opposite direction with a big frequency and then decaying to 0. If that's not too clear, and there we are. See, it's slightly wrong because now it's the wrong phase. That's because we said we were doing minus signs. And there we go. We can see we have our original function with no aliasing because this is our analog function. We have our sample points as the dots. We then have our reconstructed function, which is the dots and the lines joining them. And then we have our reconstructed waveform, which is what we'd get if we read the Fourier domain, discrete Fourier domain, and then calculated a sinusoidal function based on this. And if these were cosines instead of sines, you would still be able to reconstruct this because this would be real instead of imaginary. But we can see clearly what's happening with aliasing. As the frequency increases, the wave increases and our sample points start to become quite sporadic. But we can still always reconstruct a sine wave through them because there's only one sine wave that fits perfectly through all the way. This is the lowest value sine wave that fits perfectly between all of these points. But as we increase our frequency beyond the Nyquist frequency, so half the sample frequency, it becomes impossible to reconstruct the original signal because there is now another lowest value frequency sine wave that will fit through all those points uniquely. So I think this is really, really nice. Last thing to do is to update our text objects. So remember, we had this text object in the top left. That was a representation of the current frequency. Go ahead in there, just add text.setText, and then we'll do an f string, and we'll get it to say f equals, and then we're going to do it relative to the sample frequency. So it's going to be the current frequency, which is freq, divided by the sample frequency, so the maximum sample frequency, and then we'll do that to 2 decimal places. Have a look, and there we go. We've got a nice representation of what's happening. You'll notice as well as animation is silky smooth, so I've done a few videos where I've done animations in Matplotlib, and I've even got one video where I just dedicate the entire video to making a Matplotlib plot as fast as possible. And for things like animations, blitting is the way to go because of predefined axes. We know exactly what all of our data is. So by enabling blitting, we end up having these silky smooth plots that end up plotting really fast. Now it's a fun exercise, let's have a look. So I said, let's see what happens when we alias even more. So there's always a thing about folding, you always say, oh, half the sample frequency. What happens if we just keep increasing the frequency? What actually happens? And this is where the idea of folding comes from. So you can imagine a piece of paper folding in and itself. So where we had our f plot, let's go ahead and do something nice. Let's do f plot 2, because we don't want it to slow down in the middle. Do you know what? Let's comment that out. And then let's just do a linear space. So fplot for now, fplot numpy.linspace, and we're going to go from 0 to, let's do twice the maximum sample frequency now. Still go over n frames, so it will be faster, don't want that. Let's try it. And again, run into the same problem. We need to ensure it's an integer multiple of the frequency spacing of the original function. Which you can sort by doing that. So let's have a look now. That's our first aliasing point. You see, we also get a phase reversal. We started off with minus sign, we end up with a sine. It comes back and we go back to minus sign. And again, we get another phase reversal. That didn't work this time. So ignore the second lot of phase reversals because we haven't put in a guard in this function down here, which says what happens when the frequency exceeds a certain value, whether or not to phase reversal again, but you get the idea. You can see that this frequency here keeps increasing, whereas this bottom frequency down here just keeps oscillating between 2 states. Now I started quite easy actually, just doing a modular operator, so doing the modulo of the frequency with the sample frequency instead of just using the sample frequency. What we see here. Now, the frequency on the top keeps increasing. You get our first fold, which happens in the middle, where we get our phase reversal and the frequency starts going down. And then our frequency starts to go up again upon the second fold, so when we reach Fs, when we reach Fs equals 1.5, you get another fold, followed by with a phase reversal, etc, etc. So it just keeps folding back in on itself. So it doesn't matter what this frequency at the top is, even if it keeps increasing, you can only get the recovered aliased frequency. So here you see we have Fs as the frequency, but we would measure 0 as our frequency. 1.5 times Fs, we'd still only measure Fs over 2. Fs increment at 0.5, we read 0 with a phase reversal. And for every Fs increment starting at 0, we read 0. So I think this has been quite interesting. The last thing to do with this would just be to save each of the frames, plot frames in a folder, and then create an animated GIF from them. I have plenty of videos on my channel about turning a image sequence into an animated GIF, so I won't do that in this video. This is probably where I'll stop it. It's gone quite long, but I hope you found this interesting. And again, it just stems from one of these moments where you go on Wikipedia and you look up something and it's a time-based phenomenon, so it's on about frequencies, Fourier domains. So to me, that always says it's a time-based phenomenon. You know, it's just something's changing in time, and yet you go on the Wikipedia page and you see there was one animation, but it didn't really explain something like this. And so I like to just go along, let's just step back, try and understand it better by just writing a simple bit of Python code to try and understand it, and then making a GIF from that. So I hope some people watching this have at least learned something. Perhaps it's helped, even if it's just helped one person to sort of visualize the aliasing effect a bit better, then that's probably a good win for me. So yeah, thanks for watching this, and I'll probably do more videos like this. I find them quite interesting. Thank you.